All right, so this video we're going to be starting on energies and really just get into respiration. But the focus of this video is going to be first and foremost, what is ATP? So before we start about respiration and photosynthesis, you do want to remember these terms. Catabolic means you're going to be breaking something down. So in terms of this, you're actually going to be releasing energy. And that really goes to a couple of different key concepts, but a lot of this has to deal with when these bonds get broken down. So if you think about what is a catabolic pathway, that would be something like cell respiration, right? You're taking that glucose, and then that glucose actually is going to get broken down into a couple of things, CO2, but one of the byproducts and the payoff is going to be that ATP. Anabolic, just that word in terms of what is that anabolic pathway? You're actually going to consume energy to build complex molecules. Protein synthesis is one for sure. When you think about energy, where it's coming from, in terms of protein synthesis, the energy form is really going to be coming from ATP. But if you think about things like photosynthesis, energy can come in forms of sun in terms of the light energy. But also in photosynthesis, remember, it also still takes ATP for the Calvin cycle. So just understand that when you get into this unit, in terms of breaking or making, catabolic means you're breaking something down. You're actually going to be releasing molecules, or I should say releasing energy. Anabolic means you're really building something up. So in terms of this is kind of a nice starting thing I like to kind of go over and remind you that when you think about energy, a lot of you guys can relate to food and foods you consume. So this just shows you it's not just carbohydrates that are going to be specific in terms of how you can actually make ATP. Now, most of the time, if you do have carbohydrates, you're going to break those carbohydrates down into the individual monomers of glucose, right? So this is a nice polysaccharide. It gets broken down into glucose. Then you can actually use that to be making some ATP, and then this ATP is going to be used for cellular function. So a lot of people also kind of miss the bigger point of like, well, why do we need ATP? You know it's energy, but relate it to things that you would need to explain in this class. Well, ATP is used for a lot. It can be used for active transport. It can be used for protein synthesis. It can be used for cell signaling. ATP is used for a lot of things. Just make sure that you have a few specifics in terms of what ATP is used for. Now, this is really good to understand that if you do have some things like proteins, those individual proteins can get broken down into amino acids, and some of those amino acids can actually be used and converted into, you can still do cell respiration and actually make some ATP this way. It's just going to jump into different parts of the whole cell respiration process. Fats as well, those can actually be converted into ATP as well. And it just shows that we can actually store some as lipids. Remember, carbohydrates we can actually store as glycogen in your liver, and then you can actually store those amino acids in terms of protein synthesis. So this is just an overview about these three macromolecules can actually be converted into ATP. It's not just carbohydrates. The majority of this video, though, is going to be talking about how carbs get broken down into ATP. So in terms of this, the big thing that we need to get into is potential energy, and really it has to deal with because of its bonds. So the bonds in this case are actually going to be a key component in terms of how much potential energy they have. So you understand that it's really, really specific for you guys to make sure you feel comfortable with that. Now, we would have talked a lot more about this when we got to ecology, but again, this is just showing you that this bear is going to get some protein, some fat from this fish that he's eating, and that can actually be converted into ATP. He's going to lose some heat as some form of the energy. So like in that FRQ, remember that when you do cell respiration, a large percentage is going to be lost as heat. So just to kind of put this into context, I might have mentioned it briefly in one of the previous videos, but now is where I need to kind of make sure you guys feel comfortable with an exergonic versus endergonic. So this is Gibbs free energy. Now, you're not necessarily going to be having to calculate it, but you for sure are going to need to know what the values represent. So This basically means that if it's exergonic, that means energy is going to be released. You have less energy in your products. And if it's an endergonic process, you're going to have more energy in your products. So if you take a look at this one right here, this endergonic reaction, your y-axis is about energy. And so basically it's saying that you added in some energy and you built your final product. So if you called that glucose, and let's say this is some CO2, if you added in your energy and you actually converted it into glucose, glucose has higher potential energy than the initial reactant. And vice versa, if this was cell respiration, if your reactant was glucose, energy actually gets released, and these are your CO2s after after you actually did cell respiration. You're going to have less reaction, or I should say less energy in those carbon dioxide molecules than you did in your initial glucose amount. So know those words, be familiarized with them. So this is one thing in terms of, like, if you wanted to get into the chemistry behind it, I'm not going to emphasize it a whole lot right now. But in terms of people that are really proficient with their chemistry background, we can relate this a little bit to bond energy. It's the energy required to break a bond. So bond breaking is typically endothermic. It means you actually have to add in some form of heat or some form of energy to break it. Bond formation is actually exothermic. And it has to deal with, in terms of the bonds that get formed when you're breaking something down, that actually is going to be more exothermic. So I don't want to fixate a whole lot on that. Just know these two terms right now, exergonic versus endergonic. Now, the biggest thing about ATP is you want to remember the structure. It's a nucleotide, which means that you have your base. This is your sugar right there. So in terms of this, you're going to have your base and then your sugar, and then you're going to have your phosphates here. So remember, those are the three components that make up a nucleotide. But the biggest thing is that I want to remind you guys about what makes ATP such a good form of energy. And it has to deal with these phosphates right here. More specifically, it has to deal with this phosphate on the end, having this additional phosphate right here. Because for the most part, ATP is super unstable, and it has to deal with this last, if I numbered these phosphates, 1, 2, and 3. This third phosphate right here is actually making this thing really, really, really unstable. It has to deal a little bit with the charges. This whole thing is super electronegative. There's a lot of electrons floating around here. It's pretty unstable. But the energy release comes from getting into a lower, more stable state. So in terms of, I'll jump back here. I'm just going to jump ahead real quick. You just need to know this. ATP, like I was just mentioning, is pretty unstable. It would rather be in this ADP formation. So typically it's going to be giving this phosphate up. And this real phosphate given up, that's really, when you think about it, the energy component of ATP, losing that phosphate. So that's going to be something that is interesting. You do want to remember that. ATP is a nucleotide. Those are the three main structures: base, the sugar, and the phosphate right here. And it's that third phosphate that makes this thing really unstable. So I do need to kind of emphasize this process. Cells are going to manage their resources by energy coupling. That's a big, big, big topic you want to make sure you're understanding. So let me revisit this again. I have it mentioned in the other video as well, but if you look here, if this is your process, you're going to take glutamic acid with ammonia and you're trying to make glutamine. It gives you a delta G value that is plus 3.4 kilocalories per mole. You need to remember that that value is endergonic, right? So that means it's just going to take energy to get here. It's not going to naturally want to do that. But when you add ATP into the mix, you're going to conversion that reaction coupled with ATP hydrolysis. So that basically means in the presence of water, right? Don't forget that word, hydrolysis. ATP is going to bind to this glutamate, okay? This glutamic acid, and this creates what's called a phosphorylated intermediate. Then this is going to allow that ammonia to actually want to come and bind here, okay? And so when you break it up and look at their individual delta G values, right? This at the bottom is really what you want to take a second and understand. If you take this process, ATP converting into ADP with that free phosphate, remember this value, it wants to do this, okay? ATP typically wants to get rid of that phosphate, and that's an exergonic reaction. That this step, this one step right here, that is exergonic. So basically, if you put this together, glutamic acid plus ammonia doesn't necessarily naturally want to form this glutamine. In the presence of ATP, ATP is basically going to drive this reaction because it's more exergonic than that first equation is endergonic, so giving you the net delta G of negative 3.9. So the fact that this is a negative value, when you put these two together, the whole thing is actually exergonic, and we're also going to refer to that as being spontaneous. That means it's naturally going to want to occur in the presence of ATP. You take ATP out of the question, it's not necessarily going to be working. So I kind of have this, if you're struggling with the concepts of this, if a macromolecule is being broken down, okay, whether that's carbohydrates, proteins, nucleic acids, to their monomer, right? So you're taking a large polymer of a carbohydrate, a protein, a nucleic acid. It's typically going to be an exergonic reaction due to coupling. What is coupling? Well, that's it actually having multiple steps. If the overall reaction, meaning you added in all these steps together, if this whole thing, if your delta G is less than 0, it's going to be spontaneous. It's going to be exergonic. If you're building something, example, making sugar in photosynthesis, or we could even add in protein synthesis, due to coupling, right? If your delta G is greater than 0, that means it's a positive value. It's not necessarily going to be spontaneous. It takes energy to do that whole process, okay? So the last thing that I would need to mention about this video is, well, when you think about ATP, there's a couple of weird things that we got to address here. ATP with the presence of water, and again, it's not just necessarily going to happen. This is a little beyond what you guys need to know, but it just means that it takes enzymes, meaning ATP in water is not just going to naturally do this. It requires enzymes for this to happen. But I want to kind of show you this, that the ATP, like we mentioned, is going to be used for energy and cellular work. And basically, it's going to drive those reactions, okay? Now, I want to remind you now of these values. So this is kind of a trip. ATP and going into ADP, that means it's essentially losing the phosphate, right? So it's lost a phosphate. So ATP is adenosine triphosphate, ADP is adenosine diphosphate. So basically, you're going to have those 2 phosphates here, you're going to have the 3 phosphates here. This is going to be the delta G value of negative 7.3. That means it naturally wants to do this. This whole chapter, or really this unit, is about, well, your cells can make a ton of ATP. Well, when you look at the delta G value, actually adding on a phosphate, if you add on a phosphate to ADP, actually making that ATP, well, that's actually an endergonic process. So it's kind of a weird thing to think about, that when you're making ATP, it takes some energy, but ATP is the energy of the cell. So there's some interesting things that we're going to get into when you think about it in cell respiration. So this just shows you a more accurate representation that this is ADP, this is a phosphate. To actually put this phosphate, this one phosphate, onto that ADP to make ATP takes energy. ATP typically wants to lose that phosphate and give that phosphate to something else. So this is kind of the last summative thing on this, is which bond in ATP is most likely to break. By what mechanism is the bond broken? So this one, you have a phosphate here. It's this 3rd phosphate on the end, okay? And what mechanism is the bond broken? That's going to be hydrolysis. Because don't forget the key concept. If anytime you're breaking bonds, you're hydrolyzing it. If you were to form a bond, that would be dehydration. So explain why this reaction releases so much energy. Well, again, you're losing that really high, in terms of potential energy of breaking that bond. This bond is really, this whole end here is really unstable because of all these negative oxygens. There's a lot of electrons floating around here. So in terms of this, yeah, and that's kind of the explanation here. Negatively charged phosphates are crowded together. It makes it really unstable. And so I'm going to end this video here just on ATP.